Estimating mutual information from samples of a joint distribution is a challenging problem in science and engineering. This work proposes a hybrid method that combines the strengths of both generative and discriminative approaches to mitigate their respective shortcomings. The authors introduce a novel family of hybrid mutual information estimators that generalize both approaches, providing a tighter bound on the information due to reduced variance. Mutual information quantifies the amount of information gained about one random variable by observing another. Estimating the dependency of two random variables is a ubiquitous problem in fields such as independent component analysis, neuroscience, and Bayesian experimental design. In self-supervised learning, mutual information estimation plays a crucial role in information optimization. Classical estimators typically break down when dealing with high-dimensional data, making them unsuitable for gradient-based information optimization. Variational mutual information estimation considers a lower bound on the true information, and maximizing this bound using a flexible variational family yields accurate information estimates. The authors propose predictive quantization, (PQ), a simple generative method that can be easily combined with discriminative estimators for minimal computational overhead. PQ uses a quantized representation of the data to approximate intractable quantities, such as marginal entropy. By identifying a bound that unifies generative and discriminative methods, the authors address their respective shortcomings, providing a method that can provide more accurate estimation. The mutual information between two random variables x and y is defined as the Kullback-Leibler divergence between the joint probability density p, x, y, and the product of the two marginal distributions. In most applications, the densities in the equation are unknown or intractable, and a common strategy involves introducing a variational distribution q, x, y, to obtain a lower bound on mutual information. The authors experimentally test their models by estimating mutual information between the dimensions of a mixture of correlated multi-dimensional Gaussian distributions and compare the estimates of temporal information for a stochastic process of spatially correlated moving particles subjected to a fixed energy landscape. Overall, the hybrid method consistently improves mutual information estimates when compared to the corresponding discriminative counterpart. This paper discusses the effectiveness of hybrid mutual information estimation, focusing on the trade-offs between bias and variance in discriminative and generative approaches. It begins by introducing a general variational approach to mutual information estimation, where the joint probability distribution q, x, y, is parameterized as an exponential function f, x, y. The mutual information I, x, y, can be decomposed into two components: the lower bound IQ, x, y, and the variational gap KL, p, x, y, r, x, y, which is further split into a term dependent on the proposal r, x, y, and another term representing the estimation of the corresponding variational gap. The paper then delves into the discriminative approach, where the proposal is said to be the product of the marginals, r, x, y, equals p, x, p, y. This approach allows for great flexibility in modeling density ratios using neural network critics, but its efficacy depends heavily on bias-variance trade-offs in approximating the normalization constant. A looser lower bound for KL, p, x, y, r, x, y, is derived, which suffers from less bias at the cost of higher variance. The variance of this estimator is shown to be bounded from below by an exponential of the KL divergence between the variational distribution and the proposal. The paper also explores the generative approach, where the critic function is set to a constant, and the computation of IR, x, y, requires estimating up to 2 entropy and 1 cross-entropy term. Depending on the modeling choices for R, x, y, this can be reduced to estimating only 1 entropy and a cross-entropy term, as proposed by Barber and Agakov, 2003, and McAllister and Stratis, 2020. Popular modeling choices for joint and conditional proposals include transforming simple densities using normalizing flows. In conclusion, this research provides a comprehensive analysis of hybrid mutual information estimation, highlighting the strengths and limitations of both discriminative and generative methods. By proposing a novel hybrid approach that combines the flexibility of discriminative models with the stability of generative models, the authors aim to leverage the best characteristics of both worlds to achieve more accurate and efficient mutual information estimation. The paper discusses the effectiveness of hybrid mutual information estimation, combining the advantages of both generative and discriminative methods. It proposes a novel approach, predictive quantization, (PQ), which factorizes the joint distribution into a product of marginal and conditional distributions. This allows for tractable estimation of mutual information while reducing variance. The approach involves sampling from a discrete quantization of the variables and using a neural network to refine the proposal distribution. The paper also reviews related work on variational mutual information estimation, highlighting the trade-off between bias and variance in existing methods. It then presents an empirical evaluation of the proposed hybrid models on challenging tasks, including a correlated mixture of normal distributions and a discrete time particle simulation. The evaluation compares the performance of several discriminative mutual information estimators with and without the PQ component, demonstrating the effectiveness of the hybrid approach in reducing variance and improving estimation accuracy. The paper discusses the effectiveness of hybrid mutual information estimation by combining discriminative and generative methods. It proposes predictive quantization, (PQ), a simple generative method that improves discriminative estimators. The authors demonstrate this through experiments on two challenging tasks. They first discuss the importance of accurate mutual information estimation, highlighting the limitations of current methods. They then present an overview of main generative approaches to mutual information estimation and their requirements. This is followed by a detailed analysis of the effectiveness of hybrid estimators, including the addition of a generative component to purely discriminative models. The results show that hybrid estimators improve upon their discriminative counterparts, with the PQ method providing the best estimates. The paper also discusses the impact of batch size and number of clusters on the bias and variance of the estimators. Finally, it concludes by highlighting the potential for future work in this area, particularly in addressing the limitations introduced by the interplay between the two components of the hybrid approach. Mutual information estimation is a fundamental concept in information theory, and various methods have been proposed to estimate it. This paper reviews the literature on mutual information estimation, focusing on hybrid approaches that combine different estimation techniques. The authors discuss the strengths and limitations of various methods, including variational approaches, noise contrastive estimation, and contrastive Fenchel-Legendre optimization. Variational approaches, such as variational inference with normalizing flows and variational information bottleneck, have been widely used for mutual information estimation. These methods optimize a variational lower bound on the mutual information, which can be computationally efficient but may suffer from biased estimates. Noise contrastive estimation, on the other hand, involves training a neural network to distinguish between samples from the joint distribution and the product of the marginals. This approach has been shown to provide unbiased estimates of mutual information but can be computationally expensive. Hybrid approaches combine different estimation techniques to leverage their strengths. For example, the authors discuss the use of contrastive Fenchel-Legendre optimization, which combines the efficiency of variational approaches with the unbiasedness of noise contrastive estimation. The paper also reviews the literature on the limitations of mutual information estimators, including the work of Song and Ehrman, who analyzed the limitations of variational mutual information estimators. The authors highlight the importance of considering the trade-offs between estimation accuracy, computational efficiency, and the choice of estimation method. Furthermore, the paper discusses the applications of mutual information estimation in various domains, including representation learning, reinforcement learning, and generative modeling. The authors highlight the importance of accurate mutual information estimation in these applications and the need for further research on developing more efficient and accurate estimation methods. Overall, this paper provides a comprehensive review of the literature on mutual information estimation, highlighting the strengths and limitations of different approaches and discussing the importance of accurate estimation in various applications. The authors explore the effectiveness of hybrid mutual information estimation, citing relevant studies in the field. They provide a comprehensive notation and convention guide, outlining the representation of random variables, expectations, Kullback-Leibler divergence, mutual information, and entropy. The authors then delve into discriminative mutual information estimators, summarizing the objectives and parametrized critic architectures for various methods. They present the NWJ estimator, which involves computing the difference between the logarithmic expectations of the critic function g phi, x, y, and the proposal distribution r, y, x. The MINE estimator is also discussed, which uses a logarithmic objective function and a running average of the exponential critic function. The info NCE estimator is presented, which employs a logarithmic objective function and a softmax critic function. The JS estimator is also mentioned, which utilizes a similar approach to NWJ, but with a soft plus critic function. The authors highlight the importance of these estimators in contrastive representation learning, citing studies such as Sordoni et al. 2021 and Xiao et al. 2021. They also acknowledge the works of Van den Oord et al. 2018 and Ziebantar et al. 2021 in the realm of representation learning. Throughout the discussion, the authors utilize precise mathematical notation, defining key concepts such as the Kullback-Leibler divergence, mutual information, and entropy. They provide clear explanations of the various estimators, detailing their objectives and architectures. The summary efficiently conveys the author's expertise in the field, presenting a comprehensive overview of hybrid mutual information estimation and its applications in machine learning. The paper discusses the effectiveness of hybrid mutual information estimation, focusing on the NWJ plus info NCE and SMILE estimators. It begins by defining these estimators, with NWJ plus info NCE using an interpolation of the baseline used in NWJ and info NCE, and SMILE estimating mutual information similarly to MINE but with value clipping inside the exponential. The parameters are updated using the same objective as JS. The paper then provides proofs for the variance and an improved bound. The variance proof shows that it grows exponentially, while the improved bound demonstrates that including a set of attainable critics f can result in a lower bound at least as good as a fully generative approach. In terms of experimental details, the architectures used for the normal mixture dataset consist of MLPs with hidden layers of 256 and 128 hidden units with ReLU activations. For the discrete time multi-particle simulation task, trajectories are generated using the log density of a mixture of normal as an energy function, with specific values for epsilon and beta. The entropy is re-estimated by binning 2m samples into a 100 by 100 grid, and each trajectory is obtained by considering 100,000 consecutive samples after an initial burn-in of 100,000 samples. The paper also presents additional experimental results, including the effect of increasing the number of samples from R, Y, X, used to estimate the normalization constant for several discriminative mutual information estimators and their hybrid counterparts. The introduction of the PQ generative model significantly reduces the variance of the estimators, with a similar effect to increasing the number of negatives by a factor of x64. The paper explores the effectiveness of hybrid mutual information estimation, a crucial concept in machine learning and information theory. It begins by discussing the visualization of a 2D energy function U, x, and its corresponding simulated trajectory for one particle, as depicted in Figure 5. This visualization aids in understanding the underlying principles of mutual information estimation. The authors then delve into the impact of increasing the number of negative samples on mutual information estimation, maintaining a fixed batch size of 64. They present their findings in Figure 6, which reveals that the MINE estimator transitions from overestimating to underestimating mutual information as the number of negative samples increases beyond 4. This insight is significant for researchers seeking to optimize their estimation techniques. In addition to this, the paper also compares various estimators such as MINE, NWJ, JS, and PQ, both discriminative and generative, in terms of bias and variance. The results indicate that the choice of estimator can significantly influence the accuracy and reliability of mutual information estimates, with some estimators demonstrating lower bias and variance than others. Moreover, the paper highlights the importance of considering the trade-off between bias and variance when selecting an appropriate estimator for a given task. It emphasizes that while reducing bias may lead to more accurate estimates, it can also increase variance, potentially destabilizing the estimation process. Finally, the paper concludes by discussing potential limitations and future directions in the field of mutual information estimation. It suggests that further research is needed to develop more robust and efficient estimators capable of handling complex datasets and high-dimensional spaces.